What we have learned about the Broglie wave is that particles do have a wave property, a wavelength of h by p. P is the momentum, and if I convert that momentum into energy, it will be h by square root of 2me classically, and it will be hc by square root of ke multiplied by ke plus 2mc square relativistic. So we derived that in the last class. Okay, so my question is, what is the Broglie wavelength of an electron accelerated by 100 keV potential, 1 megavolt, 100 kilovolt, 1 megavolt, 100 megavolt of potential? So we know that if I accelerate an electron through by a potential difference between V2 and V1, the electron will accelerate with that energy E into V2 minus V1. That is the difference. That is the definition of potential difference. Potential difference is work done on a unit charge. So if I do a charge E, the work done will be EV. So that's it. The work done on the electron, and that will be the kinetic energy of the electron. And that's how the electron volt energy is defined. That 1 electron volt is an electron passing through 1 volt of potential difference. That is 1 EV. So an electron passing through 100 kilovolt of potential difference, the work done will be 100 kilo electron volt, and the kinetic energy will be 100 kilo electron volt. So if I substitute this, the electron accelerated by 100 kilovolt in the classical result, so we'll get this. We remember electron's rest energy is this. So when we do a calculation, relativistic or non-relativistic, we'll think about how much the kinetic energy is comparable with the rest energy of the electron. If the rest energy is comparable to the all are comparable, this is little bit less, 1/5 of rest energy, and this is double of the rest energy, and this is very larger than this rest energy. So for this 100 kilovolt, we'll do the both classical and relativistic, and you'll see how much is the difference between the two results, this and this. So if substitute this first, that 100 kilo electron volt of energy in the classical result, then if you do the calculation by yourself, I've already written it there, the result will be around 0.38 Armstrong, 388 Armstrong. So here, and if we do a relativistic calculation, that's hc by square root of ke by ke plus 2mc square. So there mc square is 0.511 MeV. I will write everything. Whenever I do relativistic calculation, I'll try to write everything in unit of kilo electron volt or mega electron volt. Mega electron volt will be better. So I write this Ke and Ke plus mc square all in the unit of MeV. Why I write MeV? I will substitute this hc result in MeV. I will write everything in MeV, both here and here. All units in any relativistic calculation, I will use the unit MeV. So hc, you remember this results, it will be better, any one of that. H bar C is 197 × 10 to the minus 5 MeV Armstrong. Means it will be 197 MeV Fermi, MeV femtometer, because 10 to the power minus 5 Armstrong is 1 femtometer. And if you don't use that H bar, that HC will be 1240 into 10 to the minus 5 MeV Armstrong. So if you just use this HC result, 1240, so I write that 1240 10 to the minus 5, 0.132 Armstrong. It will be 0.3 341 Armstrong. So see, this is more accurate, this relative history, and this is classical. So you compare this and this, you get a around 10-15% difference when we are using relative history result for 100 kilo electron volt. So that 1/5 of rest energy, Ke equals to 1/5 of rest energy, gives around 15% error in classical lambda. Okay. And if you do any calculation beyond that 100 kilo electron volt of the rest of kinetic energy, you'll of course always use this. You don't use classical result. So my main motto is to write use lambda equals to 2me when the kinetic energy is 1/10 is less or equals to 1/10 of rest energy. Remember this, and use lambda. Sorry, I wrote this wrong. Lambda is h by and use lambda is hc by ke to mc square when ke is greater equals to 1/10 of rest energy. Okay, so I do this part. If ke, see, this will be very simple. Ke is 1 MeV, so then lambda is for electron. Of course, we are all dealing in this problem is about electrons. So lambda is 1240 into 10 to the power minus 5. That is the value of Hc in Armstrong. And this kinetic energy is 1 MeV, and this is 1 MeV plus 1.22 MeV, square root of this. So it is 1240 by square root of 1. No, not 1. This is 2.22 square root into 10 to the power minus 5 Armstrong. That could be done. So if Ke as 100 mega electron volt, that lambda will be 1240. And if you see that when kinetic energy is very high, that rest mass effect is very less. This will be 1240 by square root of 100 into 100 101 point. No overwriting, man. Any overwriting is very trouble in this format of writing. No, I should not write any overwriting. So this is 100.22. So this is approximated as 100. So this is divided by 100. It will be 12.40 into 10 to the power minus 5 Armstrong. So as the energy increases, as the kinetic energy increases, the effect of rest mass is very less. and of course the lambda will be get shorter and shorter and shorter. As the energy is low, the wavelength is high. So the main cracks will be using in latter part of physics is as Ke increases, Ke become more dominant, as you see in the expression, more dominant than rest energy, of course, and as Ke will be less, the effect of rest mass will be higher. It's simple mathematics. But as you know, when you do some applications in daily life, we understand the meaning of the mathematics better. So that's the Broglie example, the calculation of the Broglie wavelength. You can calculate the Broglie wavelength for many other type of system. So if I just give you some snapshot, like an homework, so you do that. This would be a small homework. This is just a Arthur example. You do another homework. This is again Arthur example. These are very simple. So for this very small lesson ends here, and the next lesson we'll be learning phase velocity and group velocity of the Broglie wave. So I stop this lesson right here.